Good morning to all. So first of all, I would like to thank Baba Farid College of Engineering and Technology, and especially to Professor Sarao for inviting and giving me this honor to address the first session of this FDP program. So I feel that will be a very great initiative because I have given so many talks when recently, especially post-COVID, there is a trend for giving online talks. But I feel that the connect what you have with the offline or in person, so even you can't have even 25% of what you can get in online mode, because whenever you have an online talk, we are engrossed in other activities. There's a phone calls or other stuff. So and then there is only you're talking to a screen. So there is no physical eye contact or something, and you don't get to know what's the impact of the personality, how to have a dialogue. It's only typically a monologue. So let's start with the first talk. So the talk is Industry 4.0 past and present. So I'm a specialist in robotics area. So and robotics, one of the key elements of Industry 4.0 is robotics. So the talk will be slightly modified like this way: robotics in Industry 4.0, because it's part of Industry 4.0. But my main focus will remain on the robotics part, and I'll let you know through number of applications, number of videos, number of research areas, number of students working under me. There are more than 150 students working under me as UG students, more than 10 to 12 students working as PhD students. So what they are doing, what are the different directions, how those different directions pose different kinds of challenges, and how those challenges, as well as you can say the future, how they'll cater to societal needs and how they become opportunities. So even you can see the theme, if I could recall. So there's challenges and opportunities. So we'll try to discuss this, that how those challenges become opportunities and how those opportunities should be grabbed by choosing a right mentor and choosing a right direction and then working in that direction. So in this talk, I'll talk about some latest research directions like human motion capture, which is one of the very open-ended research area worldwide, not even in India. You go to any university, you go to Stanford, you go to MIT, you go to UNSW. I have visited so many universities. So this is one area, assistive devices and the human motion capture. So which you can say, do you name the university, you will find a research group, a very active research group working in that direction. So then we'll talk about medical robotics. We'll talk about reconfigurable robotics, and then we'll talk about some autonomous vehicles, AMRs, autonomous mobile platforms. So that will be the flavor of the talk, will different research directions. And so this talk will be outlined, like we'll start with the Industry 4.0, how its evolution. So how robotics came into existence with the Industry 4.0, its past and present. So then high-end research directions in the area of robotics which cater to Industry 4.0. So as I mentioned, all the names. So then we'll discuss the different research directions. Then we have had recently the Center for Excellence at AICTE in the area of robotics, and then a couple of my society, Mars society activities. So coming to the first part, Industry 4.0 introduction, we know it's all about fourth industrial revolution, which caters to CBS, cyber physical systems. It's about AI, artificial intelligence, it's about machine learning, it's about Internet of Things, doing things remotely, especially after COVID. It's all about automation, and so the moment you have automation, the robotics come into picture. So evolution from mechanizations to smart dedicated and autonomous systems which have the capability to take their decisions. So that's the biggest part. So how the robotics has changed from the past, you can say 50 years into the last 10 years, the main challenge lies over there. That's the power to take decisions, power to go autonomously, power to handle different directions autonomously. That's how the robotics has evolved in the last 10 years, and India is no far behind. If you see before 10 years, hardly you can find out any industry, robotics industry. But if you now, in the last 4 to 5 years, there are more than 50 startups or 50 industries, and 4 or 5 of them are doing a wonderful job in Indian context. So evolution, we can see Industry 1.0 is mainly about steam engines and mechanization. 2.0 is about mass production, electricity, assembly lines. 3 is more about, from electrical we went to electronics, computers, automation, data acquisition, charts. Whereas the Industry 4.0, which is the current context, is about IoT, Internet of Things, AI, ML, cyber physical systems, and robotics. As I mentioned, the robotics is the area which I'll fit in over here, and I'll connect with the Industry 4.0. So my keyword is the robotics. That's why it's the only word which is red in color. Rest flavors, rest keywords, maybe during your next 5 days, the different speakers will talk and connect with different keywords, right? So the first is regarding mechanization, where you can see the evolution becomes with the textile industry, with the looms and steam engines, where more conventional mechanical type of automation came into existence. Then the second industry opened 2.0, where you have more of electrical stuffs, like you can say basic cassette players, you have mass productions, transportation, electricity, even telephone. So where you can now connect the people from a far distance. So you have light bulb. And then Industry 3, where there is a digital revolution. So there is a internet. That was a third major revolution which happened. Space explorations. So then there is an innovation in the form of PLCs. There is an innovation in the form of computers and microprocessors, advanced electronics, data acquisition cards, and like SCADA, whereas you have supervisory control type of stuff. And the latest one, Industry 4.0, where is everything you want to control remotely and based on more decision power. So with this you have Internet of Things, artificial intelligence, cyber physical systems, robotics. So AI and ML, human robot collaboration. So we'll discuss on this, what do you mean by cobots and how they are different from robots, right? So this is the like Industry 4.0. You can see a typical scenario of different industries, where you can see the first robot doing the MIG welding operation, where typically the earlier scenarios you have the operator doing the welding operation, but now the center one you can see, this is the Tesla factory. Tesla, you know, one of the leading car manufacturers. So over there you can see the assembly line. So it's all occupied by robots. So what else automation you can think of? There is no bigger company than Tesla. So then you can see robot doing material handling, packaging, then all that kind of stuff. So all this, the industry, the latest industry, and how the robots have, you can say, modified the work culture in such kind of industries. So this is the robots in the past, because the flavor of the talk is industry past and present. So what happens in the past is typically you have the robots which are very bulky in nature. The weight of the robot is 50 kg, 100 kg, 200 kg, and the typically they are used for welding operations, or they are used for spray painting, or very big kind of assemblies, or packaging, or shifting from here, palletizing. So that kind of operations were there typically in industry when you call almost you can say the last 1960 onwards till 2000 or 2010. So most of the robots are being used for welding, spray painting, palletizing, warehousing. But now you talk about whatever field you can think of, robots are there at all places. So there is no survival now without. That's the future of robotics in industry. So this is the robotics at present from 2010 onwards. In the last, you can say 10 to 12 years or 15 years, you can see that's all kind of stuff, all kind of, you can say Google, Flipkart, Amazon. So all these kind of warehousings. So they deploy robots for all kind of warehousing. All the material will be stacked, all the material will be taken and maybe delivered through robots. So the second one, you can see the Vinci robot. So the Vinci robot is the one where you can have the medical surgery with the help of a robot. So the medical surgery, the robot, you can say the same, but in the perspective of robotics, it plays a very vital role. That what's the speed of response and the, you can say, steady state error of the robot. So if you deploy the same robot, let's say at the 200 feet road, like the way the Bathinda road. So if you deploy the robot for, let's say, to paint the center lines, so that there is a demarcation. So you can say on a 200 feet road, this is a typical example I used to give when I have to convince the students that why not a single robot can be deployed for all such. Let's say that I can say that the Vinci robot at present is a very good robot. So why not we should deploy it at all scenarios. So like one robot is doing the painting job at this laning in express highways. So on a 200 feet road, you can see if there is a error of even 5 centimeter, it doesn't make any difference to a bus or a truck to a trawler that there is a 5 centimeter difference. Still the lane can be maintained. But think about the same robot doing something in gold jewelry, or something, the same robot making a cut in the open heart surgery. So then open heart surgery, even 0.005 mm tolerance will be more. So over there you can't say that it's a 5 centimeter tolerance. So that's why the robot which is being deployed for spray painting might be costing 15 lakhs, and the robot like the Da Vinci which is deployed for medical surgery is of costing 15 crores. Even the degrees of freedom are same, everything remains same. The key difference lies in its accuracy, repeatability, and the, you can say, precision. So you cannot expect that you can have a medical surgery from a spray painting robot. So that's the difference. The third one, you can say, the humanoid robots. The fourth one is the autonomous mobile robot working in agriculture. So a lot of agriculture is being done using robots. So then you have inspections, for rescues, for even you can see even across the border, for defense purposes, for mining, for space explorations. So you talk about any area, robots are there. So that's what's the journey of the last robots in the last 10 years. Even you can see all at hospitals, even at multiplexes, convention halls, airports. So robots are communicating with people. So they are being the mode of transports. So catering to this, what's my robotics journey from the last 2 decades? So we'll try to give you some flavors. So regarding this, I have some active online collaborations in the field of exoskeletons and wearable devices, in modular manipulators, in flexible manipulators, in assistive devices. So in the domain of exoskeletons, we have active collaboration with the University of Gävle, Sweden, where I went there as a visiting faculty from 2015 onwards. It's a collaboration active from the last 10 years. With IIT Gandhinagar, we have a huge project with IIT Gandhinagar. With the University of Queensland, Australia, we are again having one ongoing project. So with the modular manipulators with IIT Ropar, with the flexible manipulators with IIT Delhi and CSIO Chandigarh, with the assistive devices with the DRDO, DEBL and State University of New York, USA. So these are the active collaborations in the last 10 years what I used to have. So in this all directions, one thing is common, that is controls, the robotic control. So that is the backbone, or you can say the key area which thrives all this, because robotics, it's all about dynamics and control. So you need to understand the theory, the mathematics, the dynamics behind. So certainly this talk is not about dynamics, but sometimes if we encounter sometimes in future, or maybe I have a YouTube channel over there, you can refer to my lectures on dynamics and control part. So the dynamics we are not going to cover, but the impact of dynamics we are going to cover over in this lecture. So these are all connections. So then this is all talks being delivered, more than 100 talks within India and across different countries. More than 20 countries I have delivered the talk. More than 80 venues within India have given such talks at various IITs, NITs, CFTIs or other university or top level labs. So this is the research innovations by my group in the last 8 to 10 years, where the first one is, as I mentioned, in the area of exoskeletons. We'll cover this. The second one is in collaboration with the IIT Ropar modular manipulator, where we can see, the second one we can see, where instead of making a single arm, we are making a library. So the library is modular in the sense that you can combine the different modules and come up with a new configuration of the robots. So otherwise what happens that we have seen there are companies selling the same robot with a different gripper, telling it as a welding robot, and changing the gripper and selling the new robot and telling it is a painting robot. And the cost of each such robot is 50 lakhs. We have 2 such robots in Thapar, KUKA robots. I will show you. The cost of each is around 50 lakhs. The basic arm is same in both, but the companies are not giving that, okay, change this gripper and something. They are selling one as a welding robot, one as a milling robot. So this is where this kind of a modular library will be very handy. And with this library, if you develop such a library, you can build any kind of configuration out of the robot. The third one is in the field of medical robots. We'll try to see like the way you have laparoscopic operations. So how to handle such kind of operations. The fourth one is in the field of you can say surgical robots. So this is the stuff what my group is doing from the last 10 to 15 years. So we'll cover some of this, not all, some of these directions, and I'll just. So the first direction, which is very you can say open, and the research from if you happens to be this kind of research area, the funding from the government and the ease with which you can collaborate, because this is one such area which doesn't seek any attention. So that's the healthcare. So healthcare is one area where the prime focus of the government is in the area of healthcare, and you go to any foreign university, so the healthcare is the one where you find there's a lot of research is being going on. So this is the first area, assistive and wearable devices. So over here you can see assistive and wearable devices means typically being used in the past also. So you can see to enhance the power of maybe a worker or a soldier. So typically if you see, we typically have exoskeletons. The exoskeleton name is built using the word exo and skeleton, where exo means external and the skeleton means something which is to enhance the power, to augment the power. So typically natural skeletons, you always in all kind of, you can say nature, you can see in tortoise, in all kind of reptiles, you have this natural exoskeletons. In humans we have endoskeletons because of our bone structure, because we have bones for internal strength. Whereas on the robotics front you have all kind of exoskeletons, maybe say hand exoskeleton, upper body exoskeleton, lower body exoskeleton. And all these exoskeletons are typically being used to tackle muscle strength, which may be weak because of either aging, or there is some neuromuscular disorder, or there is a power augmentation required for soldiers or workers working in the industry. And typically why you need exoskeleton? Because the conventional methods, like you might have seen for old age people, either they use the sticks or walker or wheelchairs. So these are the conventional methods, but these methods have their limitations, because over there you always need house help or nurse. Second thing is, there is a, like if you want to stair, climb up, climb down, then there is an issue. If there is a uneven terrain, then there is an issue. So all these issues can be catered with the help of exoskeleton, which is like this. So need for exoskeleton is, as I mentioned earlier. And then on healthy people, like for soldiers or workers which have to carry very heavy payload repeatedly, maybe let's say 50 kilogram of payload. So for that, normal people can, let's say, have 20 to 30. With exoskeleton you can have 60, 100, 200 kilogram payload you can carry. So this is a typical figure of exoskeleton, where you can see there is a wearable device. The wearable device is having some battery, some joints, some actuators, some sensors, some kind of machine learning, some kind of AI. So typically the exoskeletons are being classified into multiple categories, but typically they are classified as medical or non-medical. Medicals are one where just the patients have some kind of medical issue. There could be some muscular disorder or some spinal cord injury, so that is there. And for the non-medical ones, the typically is for used for either soldiers or for workers to augment or to enhance their weight carrying capacity. So my area of research is typically at present is under non-medical, active and lower limb. So this is, like you can see, hip exoskeleton, knee exoskeleton or ankle. So just a flavor of what do we mean by over here. So typically when you have to work for exoskeletons, typically because the way you walk, so we typically walk in 3 planes. So we restrict ourselves that when you are talking about exoskeletons, let's restrict our movement to frontal and back plane, which is called as the sagittal plane. So the way you walk front and back, so that plane is called as the sagittal plane. So this is the plane what we are talking about. And if we restrict our movement to sagittal plane, the angles which are important is, you can say, extension and flexion of the hip, extension and flexion of the knee, or dorsiflexion of the ankle. So these are the angles which are important, whereas the other angles are also shown, which we are not considering while considering the sagittal plane movement. So this is a typically, you can say, the scenario of motion capture lab, where you can see there are number of IR cameras which are mounted. There are 6 to 8 cameras, with which the beauty of this camera is that they can detect the joints, and you can find out you have IR markers, infrared markers, which you can paste on your body, and it can detect the markers. And you can say the accuracy and precision of those video cameras is so high that you can find out the joint trajectories, that how your hip is moving, how your knee is moving, what is the trajectory as a function of time, that you can calculate. And also there is a force plate, we will come to that also. So then, talking about the exoskeleton, first of all you need to understand what do you mean by the human motion. So human motion is basically called by a gait cycle. Gait cycle is called as a pattern, the way we walk. And this gait cycle is being classified into 2 phases. The first one is called as the stance phase, where your feet is grounded, which is typically 60% of your gait pattern, and the swing phase, where the feet is in the air. So like this way you can see, here you can see. So the feet either is grounded or the feet is in air. If we talk about the only right leg, which is a black portion, so this gait cycle is being classified into this 7 to 8 categories or stages, starting from initial contact where your heel first strikes the ground. You can see the black portion, black leg on the circled image. The gait cycle start with the heel strike, so then it's called as the heel rise, then you call it the toe off, and then the other stages. So all this you will have to develop the dynamic and kinematic model. So for dynamic model we have this gait lab. So this is the general gait lab, whereas the right hand side you can see the gait lab being developed at Thapar University. This is a 1.5 crore funding, the investment required to have this gait lab. So this is like this way. You can say just one small 30-second video.
Hello everyone, welcome to our gait lab. In this video, I will give you a quick introduction to the major hardware we use in the Qualisys gait analysis system. These tools help us capture and study human movement with high accuracy. The first and most important hardware is the infrared camera. These cameras emit infrared light and detect reflective markers placed on the body. Unlike normal cameras, IR cameras can track motion in 3D space with very high precision. In our lab, we have multiple Qualisys IR cameras placed around the room. By combining their views, the system creates a complete 3D model of human movement. The next important component is the marker. These are small reflective spheres that we attach to specific anatomical points on the subject's body, like the hip, knee, or ankle. When the IR camera light hits them, the markers reflect back, allowing the system to track joint angles and body segment movements accurately. Another key piece of equipment is the force plate. In our lab, we use the AMTI force plate. It is installed on the floor and measures ground reaction forces when a subject walks, runs, or jumps over it. This helps us understand balance, gait patterns, and load distribution on the feet. The force data combines with motion capture data to give a complete picture of human movement. To ensure all cameras and markers are aligned in the same 3D coordinate system, we use a calibration set. This usually includes a calibration wand and a reference frame. Calibration ensures that all recorded data is accurate and consistent across the lab setup. All these hardware components, the IR cameras, reflective markers, AMTI force plate, and calibration set, work together. When a subject walks inside the lab, cameras track the markers, the force plate records forces, and the calibration keeps everything.
So the cost of this you can say Qualisys gait lab is around 1 crore, and the cost of one single force plate is around 22 lakhs. So sometimes it's not easy to have such sophisticated stuff. So if you want to see the demo, if you want to have some research in this direction, please feel free to contact me. This is, as I mentioned, state-of-the-art world-class equipment, where you name any university, I can tell you this is the person working in this direction, right? So the data coming from the marker, each one of the marker will be for like this kind of Excel file, where you will get the X, Y, and Z coordinate data. So this data can be mapped with the help of forward kinematics. So we have validated our MATLAB code using MATLAB and the kinematics. This is right knee trajectory, right knee trajectory in the Z direction, then ankle trajectory in X direction, ankle trajectory in Z direction, and you can see that the accuracy of our model is that there are two data superimposed. One is our MATLAB code and the other is the data coming from the marker. So that shows the accuracy of a mathematical model being used. So this is how you can develop the leg model. So in order to basically do the gait analysis, the first and foremost is that you should know how to capture the human motion. So to capture the human motion, you need to model the human leg. So we'll use like simple DH parameters, which you find typically in any robotics stuff. So we'll restrict ourselves to sagittal planes. So we'll have this angle important, this angle important, this angle important of the hip, knee and ankle, because we are restricting our movement to sagittal plane. So we are limiting ourselves to only flexion and extension angle. So over here then you can find, when you model this, you can find that this kind of exoskeleton structure you can find, and you can see the real-time trajectories of the hip, knee and ankle of your human joints coming from the software, that how these will come. So then this is, you have to make a MATLAB in SimScape, where you have this the left leg body, right leg body and the upper body, and this is how you can make the model in human SimScape, where you can see as the human walks, the joint trajectories of all three major joints in real time. So this is the real-time data, how you capture the real-time data and validate this. So then we have done this project with one of the prominent lab, DRDO lab for DEBL. DEBL is a lab in Bangalore which is mainly working for in this you can say exoskeletons for their soldiers, and one of their soldiers, Jaron Francis, with body weight as 67.2 and body height as 173.5 centimeters. So because they said it's a DRDO lab, so everything is confidential, they say that we don't give anything to you, we'll just give the name of the soldier and the two parameters. The rest of the dynamic model you have to develop using your own assumptions, because rest of the data is confidential. So how to tackle such scenarios where 90% of the data is confidential and you have to come up with alternate solutions, that how to model this. So over there, so we came up with such models where you can see that the person, this black one is the zero payload data. This is the data validation with the 5 kilogram payload, 10 kilogram payload, 20 kilogram payload, and this is the band we found out that you now come with any soldier, the joint torques will come in this band only. So then based on that we developed the initial exoskeleton in collaboration with Sweden. So this is the initial design of the exoskeleton, which weighs around 35 kilograms. Second iteration of the exoskeleton weighs around 25 kilograms. And now we are at the third stage, third generation, where you can see there, this is we are doing the end user testing on treadmills for humans, which are you can say healthy elderly people. So the challenges over here, as I mentioned, is a talk, one of the keyword is challenge. So challenge over here is that how to make this as light as possible while maintaining the strength. So as I mentioned, the first exoskeleton made by this group is 35 kg, the second one is 25 kg. If you come up with a new design that we can make it in 15 kg, certainly I can give you offer, you can collaborate with me directly. So one of the biggest challenge over here is to how to cut down the weight while maintaining the strength, because this exoskeleton has to carry 70 kg human also, तो उसकी खुद की strength भी चाहिए. So if you come up with a solution that okay sir, I can design such exoskeleton which can weight means weight of the motors also. There are 6 motors. So that including those 6 motors, if you can come up with that, okay, the exoskeleton carrying 15 kg, please consult me. We can talk with ADVO, we can talk with the humanoid, we can talk with the other industries that okay, we have a solution to your problem. And maybe it's possible that you can directly being taken by the company, because now ADVO, one of the leading companies in India, have a direct you can say, order from Reliance to make 1,000 humanoids in a span of 1 year. The moment you say that, okay sir, we can make this exoskeleton which can lead to a humanoid later, I think IDVAB is looking for the right person from you if you can make something. So that's where the challenge is, and there is the opportunity also. Right? The same thing is the battery backup. And battery backup, like our phone, is the major challenge. आप जितने मर्जी power की battery ले लो, आपने देखा ही है, you might have seen. Earlier the batteries are only 700, 800. Now there are 3,000, 4,000, 5,000, 6,000 mAh. उसके बाद भी 3 महीने के बाद phone 12 घंटे चलता है. All this is just to sell, increase the sale and all that kind of stuff. But there is no smartphone which runs for 3 days. The third one is adaptability to different users. This exoskeleton is not made for a single human, then the cost is among us. This is designed to build for different people, different build, different height, different weight. So how you cater to a single design exoskeleton having same set of motors which can cater to a 5 feet person also, 6 feet person also, 70 kg person also, 90 kg person also, 110 kg person also. So what are the fine tunings you can do in the exoskeleton which can cater to different body builds, different body heights and different body weights. So here's the biggest challenge, and if you can come with the solution, please consult. Please come and collaborate. And then there is a need to develop low cost actuators, because the cost, if you talk about Maxon, the cost of one single actuator is around 5 lakhs. One single BLDC motor which can give around 50 Newton meter of torque. So one single motor costing around 5 lakhs. So if you refer that this is a company which gives, let's say, the same actuator with same kind of precision and repeatability in 50,000 rupees, we are looking for such solutions. We are looking for, so that's again I mentioned, there is a problem, there is an opponent problem, there is a challenge. Immediately there is this opportunity that okay, you can build a startup. People are looking for such motors where the cost is 1/5 of or 1/10 of Maxon motors. So with this I have mentioned you 4 such different directions to open your startups. So coming to the second area, certainly this is just I have given you the flavor, because the flavor is to give about different directions connecting to Industry 4.0. Otherwise I could have spoke for 4 hours on this single topic only, but let's go ahead and going to the next direction, underactuated and flexible systems. So underactuated means that you have such kind of flexible system where you can replicate something like elephant trunk, or you can have something like flexible system which can grasp some fragile objects, like you can have a mug or you can have an egg, you can have something like all kind of creatures or all kind of reptiles in nature have your flexible. So your dog tail, your trunk of your you can say your snake or elephant trunk, all these are your examples of flexible systems. And all these kind of flexible systems, you have different kinds of applications. Typically now you can see in the area of biopsy or laparoscopy. So what do they do in biopsy and laparoscopy? They are having a very small kind of robot which is having a camera, and it is flexible, which can go through the human veins and it can find out that where is the blockage. Similarly in sewerage plants, so where you can go and find out that you send the robot inside a sewerage pipe and it can let you know where is the blockage, instead of opening and breaking the walls and try to see where is the blockage. No. So challenge over here, you can see the moment you vibrate a flexible thing, there are vibrations, because the weight of the robot, the weight of the link is so small. So over there, the challenge over here is how to tackle this flexible structure, how to tackle these vibrations. So we developed this two-link flexible manipulator at Thapar University, and this project is closed, but this given very good results, and we had very good publications in this area. So then in the area of under-actuated systems, we have multiple control setups. So under-actuated means that you have number of degrees of freedom, but the number of motors to take care of those are less. So typically here you can see there is a inverted, you can say, pendulum problem. The linear inverted pendulum, the cart can slide in this way, and the pendulum can oscillate in the vertical direction. So here is the mathematical model, here is the experimental model. Here you can see both experiment and theory going hand in hand. And here you can see that making a simulation in MATLAB, that depends upon the accuracy of your model, and all these parameters of the pendulum are taken from the setup. So let me show you over here. So over here we are disturbing the pendulum, checking the robustness of the controller being developed. So this is then the fourth one, the irregular shape like amoeba. So the challenge over here is the number of turns it takes into account. So like let me forward this video. So here you can see on the red is the desired one, and the white one it is drawing is the actual one in real time. So how to take these sharp turns is the challenge, and that too in a very narrow space. So then the next category is autonomous mobile robots. So again the word autonomous comes into picture, and the meaning of autonomy is the power to take self-decision. That there is no one to help you out, you have to predict the situation, you have the power to take the contingency measure as per the situation. So in this direction, the commercial jargon says this term as AMRs. So in this we have working in Thapar at three different directions. One is the warehousing robot, the other one is the rover, Mars rover, the third one is called as the cleaning robot. So here you can see the scope of cleaning robot also. The scope of cleaning robot is to the each individual house. We are not talking about industry at all. Industry कितनी लगी है? 5, 10, maximum 20. And the scope of this cleaning robot is in billions. No one knows that after 5 years, जो सफाई वाले हमारे जो workers हैं सब छुट्टी हो जाए और ये cleaning robot is deployed at every house. That could be the scenario after 5 years. So this is the challenge right now. That agar if you both are working like me, both are working, my wife is working, so getting a very good maid is a big challenge. So the challenge, the word comes challenge, there comes the opportunity also. You can look for a startup in cleaning robot. The cleaning robot, the cost is, if you see the MI company, Eureka Forbes company, you get this robot in 20,000 rupees. 20,000 रुपीज़ आपकी मेड अगर 4,000 रुपये में है तो 5 महीने में आपकी कॉस्ट रिकवर हो जाएगी. So there comes the, again as I mentioned, there is a challenge, there is an opportunity, and this is the future also, that after 5 years it may be possible that all housemaid are being replaced by these cleaning robots. So we are working in these directions. I'll just show you the flavor of some stuff in this direction. So autonomous mobile robot is self-navigating robot having equipped with artificial intelligence sensors, motors in order to analyze and act accordingly. And components are all different kinds of sensors, LIDAR sensors, power systems, battery, AIML, SLAM is simultaneous localization and navigation, where it can map the area offline and can take the call and it can maneuver itself. So you have communication systems using Wi-Fi, IoT, you have onboard processors, you have power and mobility unit. So all these are very important. If you have to build your cleaning robot or your AMR from scratch at your college or at your place. And then this is how this kind of AMRs work in industry. So where you can see the AMR on the left hand side, it can go in straight line, it can detect the obstacle and it can take a counter path if it detects a path. So this is how you can see AMR. It's not only about only one cleaning robot, it's about different industries. The first one you can see AMR working in industries. The second one is AMR working in healthcare sector. The third one is AMR working in underwater. So what else space is left? All space is being occupied by AMRs. You go to all hospitals, all airports, all you can say convention centers. You will see all kind of autonomous mobile platforms now. Even cricket matches are not away, you can see. So for publicity, you can see either quadruped or AMR coming with the ball, picking up a ball. So even in entertainment industry also. So you will find the application. So here you can see the next one is the warehousing, the next one is the retail outlet, the last one is in the mining and exploration in defense sector also. So for any kind of rescue and recovery, so let's say there is an earthquake and there is a building and you find that there is in the building there are 20 people still entrapped, they are living, and instead of risking the life of our soldiers, we can deploy such kind of robots which can go. ज़्यादा से ज़्यादा क्या होगा, robot may be lost, but that's fine. Human life is much more precious. So in such kind of rescue and recovery operations, these kind of robots have enormous scope and application. And it could be, I'm not talking about industry 4, sir, I'm talking about industry 5 now. It could be leading to industry 5.0, where the robots can now find such kind of solutions which even humans can't do. No one wants to go inside a nuclear power plant or any earthquake resistant building जिसमें कुछ कभी भी गिर सकता है. So that's the power of autonomy. So at Thapar University, as I mentioned, we are making the first one in collaboration with the RoboMuse. So 3 set of students worked in 2016, went to IIT Delhi for internship. So they worked on first generation of this, second generation, third generation, and eventually they are the pillars of one of the robotic company, आपने शायद नाम सुना, Peer Robotics. So Peer Robotics is a brainchild of one of the students from IIT Delhi and 3 students from Thapar University which still are working over there in Peer Robotics. So again, the issue is autonomy, machine learning, navigation, human-robot interaction. So this is you can see the real robot while it's second stage working at the corridors at Thapar. It's called RoboMuse because it's a muse. It should work like a muse, but robotic in nature. So it can be deployed all hospitals or even in convention centers to help the people. So over there in the right hand side you can see the map being created by the students. So this map is required because you need to know the simultaneous localization and mapping SLAM. So this map you need to generate offline, and the robot can now know the location of all the chairs, tables or all other obstacles, and it can maneuver automatically. So this is, you can say, further trials on robots. Even so, this robot having 80 kg payload. Testing on speed, testing on gradient, testing on uneven terrains, testing on turning, So then this is the rover made by students from scratch by this Mars means Mechatronics and Robotics Society, where I am the president of the society, and more than 150 UG students, irrespective of whether they belong to mechanical department, mechatronics department, electrical department, electronics department, or a computer science department, all are working as tandem till the time their classes are off, 5 p.m. till 5 a.m. in the morning, without from my side giving any motivational dose. They are self-motivated, working. Sir, UG student, can you imagine working 5 a.m. in the morning? Not all, but if there is a, let's say, 1,000 students applying for Mars, we are only taking 50 into account, which has that kind of passion. So this is basically the 3 generations of the Mars rover being developed by them from scratch. You can see in the center the 2023. So then there is a modification 2024, and then there is a further modification 2025, the 3rd generation. So in the 3rd generation, this is the International Rover Challenge, which is basically an international event which happens this time at BITS Goa, where there are more than 100 teams participated, and in the 3rd year of this competition, our team got the runners-up prize, and which is a, you can say, landmark achievement for us. So that out of 100 teams from all IITs, international, even from Europe, even from Nepal, Bangladesh, all adjoining countries. So there are 100 teams, and this team got the runners-up prize. So this is you can say the real times movements or snaps taken from the BITS Goa in February this year, where you can see that the reckonings, there is a collection of some stuff in given time, and then there is a delivery, and then you can see the terrain, it's uneven terrain, going up, going down, and then there is thus autonomously that electrical panel needs to be operated. And this is the winning moment for them, the prizes and their certificates of runners-up prize. And this is, you can see the morning update, 17th, today morning, the today morning update. So how the students are passionately working for the next generation. The next competition is marked over here. It's in Manipal University and Udupi. And this is a testing being done at morning 2 a.m. So that's the passion of the students. So now you can see how they are checking the uneven terrain, or even they are checking this that from how far distance they can get the feed. So this is almost 1 kilometer away from their base station. The third video, you can see the students are around 1 kilometer away from the base station, and they are controlling the rover from their base station. So then the third point in this AMR is the cleaning robot, where you can see it's a part of only summer project, and this summer project is taken up by first year students जिन्होंने अभी course भी नहीं पढ़ा है. They have not even taken any course at all in robotics. But what dictates them, what makes them different is their passion. The passion to work, the passion to learn, and passion to deliver. And it's a work of just 40 days. So you can see in a span of 40 days, they have designed this kind of CAD model, the 3 iterations of CAD model. Why the first iteration is failed, second iteration is failed, third iteration. So from CAD model, they went to this, how the motor selection, acrylic walls, the weight of the acrylic walls. The earlier weight was 6 kilograms, then the weight is 2.8 kilograms. So then they made it with they found out that using this kind of cleaning robot comes with Xiaomi, as I mentioned, and the Xiaomi used the parts using injection molded ABS. They compared that what is their difference with commercialized projects, जो इंडस्ट्री में commercially available है उसमें क्या है, and why we can't perform or match with them. So they found that the material used by them is injection molded ABS. So they, in the latest, you can say, generation, they are working on this material. So then comes that how the cleaning robot will collect the dust, what is being done, but what is being used by commercial products, what is the roller brush, different kinds of brush being used, and then the different kinds of bags, dustbins being used by them, different kinds of, you can say, pressure measuring, because for suctioning, to detect or to collect the dust, it's the suctioning power of this is very, very important. So what kind of pump is being used, what kind of battery is being used by them. So this is the centrifugal pump being modeled and 3D printed by them in different iterations, and they have measured the pressure also. So I'm telling you the work of just 40 days. It's not the work of 4 years. I'm just showing you the work of first year students in 40 days work. But what makes them different? Their passion. So this is how they made it, the first iteration, the robot working autonomously. So the next category, again the second work done by another team in 40 days, reconfigurable robot. So the reconfigurable robot is the one where you can see the robot can change its shape. It can reconfigure itself, and it can deploy different kind of work. So over here in the first, you can say over here they worked, make it in week wise, because they have 6 weeks to work. So over here in the ideation stage, I showed you just one YouTube video. My work is to motivate them, and I spent 7 minutes to motivate them and show one YouTube video कि आप इसके close कुछ बना सकते हैं. Can you make something closer to this? And I literally have no idea that whether, okay, the students will really come up with this design and the setup in just 31st day, on the 31st day. So this is their first day. They sat and ideate, come up with the CAD design, creation of the CAD, then they come up with the electronics, they come up with the control. So over here you can see they made the first design with cardboard. Okay, why? Let's not try to waste the material. Let's try to see that whether it's possible at all or not, because they have no idea whether this is possible at all or not. So they ideate and they tried with the cardboard. Okay, they found that okay, it looks working. So then they come up with the better material. Then they found that okay, whether let's see the feasibility of electronics. Are we in a position to develop the electronics? Can the electronics, we can build something which can lift itself? Third is that then they make it a control, because this device has to be controlled through mobile. It's totally Bluetooth wireless, and it has to be controlled through mobile. So then the results they found. Then the problems faced, as I mentioned, problems and challenges are the, you can say, cornerstone for any opportunity. Wherever there is a problem, wherever there is a challenge, only then you can find there is a something to be opportunity which can be encashed. So then you find improvements, finishing touches. So then you can see this is the robot. I'll show you mode wise. So this is the linear mode. Here you can see the robot is working on one side, linear mode. Over there the robot is working in frog style. Over here the robot is lifting itself. One module is lifting itself. So this is right now we are trial of 2. You can think of the endless opportunities when 5 such modules or 10 such modules are joined. We are right now working on 2 modules, and certainly we have ample number of directions to work. It can work as a snake, it can work for rescue, it can topple, it can like go upside down, it can do anything. So in maybe the future talk I may show you its newer versions. So right now we are working on 2 modules, but the directions given to the student is let's make 5 modules now. Let's work on 5 modules. What wonders they can do, even we can't think of right now. And more importantly, they have developed everything in-house using their mobiles. This is all done, controlled using mobile. And that too by first year students. That too by first year student without any training. So then we are not showing the finished product, only we are showing you the challenges in between. So like you can see this, how they're controlling and measuring. The one is controlling the linear, that in how many turns, how much distance is being traveled. So it might be, you can see that the robot might not be going in the straight direction. That's because of the slippage of the side faceplate. But they are now counting that the faceplate with how many rotations, how much is the distance being covered. The second one is with the flip. With the frog mode, in how many strokes the distance is being covered. We are going to have this Center for Excellence at Thapar, where we are going to invest around 3 crore rupees to develop this Center for Excellence. And I visited many universities abroad also. So this is what we are trying to have. So this is currently what we have is the KUKA robot. Cost of each robot is around 45 lakhs. The left hand side you can see this one welding robot. On the back end side in the second figure you can see the milling robot. Both are KUKA, as I mentioned. Both are the same arms, one with end effector as welding, the other one as milling. So this is the second one, is the gate lab. The third one is we are going to have this cobots. Earlier you can see the robots are caged. Over here you can see the robots are in cages because it's a beast. The weight of the robot and the power is so high that the humans are not supposed to go inside the cage while the robot is working. So robot and the humans are working in 2 different spaces. So that's why they are called robots. But with the advent of technology, with the 4-stroke sensors, you are having such kind of robots. Here you can see universal robot, where they are attached with 4-stroke sensors, so that now the humans and the robot can work in the same space. So that's why they are called cobots, because they are called collaborating robots, where human and robot can collaborate, which is not possible earlier. So that's the new future area. So here I'm showing you different applications of this cobot, which we are going to have. The cost of this robot is around 35 to 40 lakhs. So this is having different kinds of grippers. So as I mentioned earlier, grippers are also hard fingered. Now the grippers are soft fingered, so that they can tackle fragile objects like egg or glass or cups. So this is a Kinova robot. Kinova is a Canadian company. The beauty about this robot is the weight of the robot is around 5 kilograms. It's made from carbon fiber. So you can put it in a briefcase and go to wherever, and you can deploy in the classroom within 4 to 5 minutes, and you can give a live demo on the robot itself. And carrying and mobility is possible only because the weight of the robot is 5 kilograms. Whereas the weight of the previous robot KUKA may be 80 kilograms. So it's not possible for KUKA to carry along. But certainly it is possible for Kinova that you can take it along wherever you want. So then the third one is the dog robot, what we are going to have, or also we are developing in-house. So this is a quadruped. It should work like a human or natural dog. So it's here all kind of, even though the mechanism is mechanical, electronics, but all kind of electronics, AI, ML, deep learning, SLAM comes into picture over here when it comes to navigation. So here you can see what the robot is doing. And you can see the power of computing, that how in real time it is processing the environment and taking the decision. So these we have ordered already 2 robots, and these 2 robots are maybe by December you can find it in our Center for Excellence. So this is how the assembly of such robots is being done. So this is then alpha humanoid robot, as I mentioned, for all kind of hospitals, all kind of convention centers. So where the humans can interact with the robots. So then this is something like a training platform where the robot can do multiple stuff. So even from something from a conveyor belt to palletizing to vision based applications. So all kind of sensors, latest actuators, later vision-based technologies are integrated in one single setup. So how to pick up, how to reorient and place it at the right orientation. So that is the challenge. So then this is as I mentioned, this is a commercial grade autonomous mobile robot जिसकी 3 applications, already 3 such applications then in-house being developed, we already showed, but still now we have this robot because this is being deployed for agriculture operations. So for agriculture means that there is a, you can see over here in the left hand side there is a rover, or you can say there is a vehicle. On this there is a arm is being deployed, and rover can go within, you can say, all kind of fields, and the arm can do multiple things, like you can say plucking of fruit or strawberry. So plucking of strawberry is a biggest challenge, that when to pluck the right strawberry. The strawberry should not be premature or it should not be overripe. So depending upon the color, texture and the flavor or smell, the robot should be able to find out that okay, this is the perfect strawberry to be consumed. So let's take out this strawberry, which is not possible for a labor or layman. So that kind of stuff can be done. It's a huge market for robots in the agriculture domain. And then there is a huge market for the robots in the vertical farming, because agriculture field, the amount of space required in the horizontal direction, everything is decreasing. So now we have to think of how to do vertical farming and how to automate that vertical farming using robots. So how to plant them, how to feed them, how to fertilize them. It's a huge scope in this direction, especially in the Punjab area where agriculture plays a very vital role. So how to automate, how to you can say support our farmers so that the output is maximum. So this is some of the, I showed you 3 activities already, some of the other activities by Mechatronics and Robotics Society. So here this is one competition they won at BITS Goa again, where basically you can see this is a BITS Goa map, and over there they give a problem that okay, there is a power failure at various power grids in the campus. So you need to make a rover which can go across the campus and find that there is a failure. So our team developed this code and this rover in online mode and won the first prize over there. So then this is their gripper. This gripper they made playing rock, paper and scissor. rock, paper and scissor, and in one of the fairs you can see the campus director, the institute director is playing rock, paper and scissor with the gripper. So then the students take into account outreach activities, they because they see very passionate students. So we'll deploy multiple workshops with students. The workshops are at school level, institute level, all levels. So where the students are very fascinated, so that they can be motivated and they can take up such good projects which have this societal impact. So then there are other workshops being conducted with the students. So this is Industry Connect, where you can see the co-founder of the ADVO, one of the leading companies in India, which is the #1 company in India. The turnover is more than 4,000 crores now. 51% stake is taken by Reliance now. It's just 8 years old company. More than 4,000 crores. So the co-founder of this, Mr. Sangeet Kumar, visited us and spent 2 hours with the students, saw different work, and now 4 students we sent for internship. So again, what's the use of doing this? All that competition and madness and overnight, because in classroom you cannot have that kind of flavor which you see in these such competitions. The hands-on experience, the challenges, the real-time scenario, and how the other teams work in across competitions, how you learn and how you make yourself industry ready. So we sent 4 students to ADVO, and all 4 of them got selected in ADVO with pre-placement offer of 16 lakhs, whereas the average Thapar packages for mechanical students is 10 lakhs. So that's what they have got from such work or such type of competitions. So this is what we are looking for, that okay, 4 साल करने के बाद मुझे क्या मिलेगा? So one is the knowledge, the other is the service to the society, the third one is you can look for your own startup, and otherwise job is guaranteed. If you have 1 or 2 such projects, I can guarantee that your job is automatically secured. So then, in all this, at the back end, there is lots and lots of mathematics, lots of kinematics, lots of dynamics, lots of control. Out of these 3 words, I have not used a single slide because the flavor is to give related to Industry 4.0. Maybe at some different podium, maybe I can talk about these 3 big terms. But if you are interested, I have a YouTube channel catering to more than 30 lectures, catering to all 3 dimensions of kinematics, dynamics, and control. So you can go through them. They are very well made videos, and these are being developed during the COVID time, and feedback from different, you can say, robotic researchers across the country has been taken and implemented, that how to make them better. And you can see that how I used to take the class previously and after that in the online mode. And then this is the number of reads of that channel, and this is not only by Thapar students, that 1.25 lakh students feed reads are there already. So this is the success stories of PG students of my last 10 years, where you can see Dr. Gurminder Singh is a faculty member at IIT Bombay. Dr. Jyotirendra Narayan is at IIT Patna. Dr. Ishan Chawla is at Jaguar Land Rover. Dr. Nisha is at YMCA. Dr. Prakhar is at Fiat, and Dr. Rohit is at SRM Chennai. This is all PhD students. This is the success stories of UG students, where all are either at ADVO or at Novus High Tech, or a couple of them are at some international universities. So acknowledgement to this big team, references, and thank you.